Good afternoon, everybody. My name's Adam Floyd. I'm a field application scientist with PerkinElmer. And today I'm going to talk about three of my favorite subjects, which are cannabis, gas chromatography, and mass spectrometry. So I'm going to talk for about 20 minutes, 25 minutes, and then we'll have some time for questions. So I've worked in the cannabis industry about 11 years, spent a lot of time doing research on cannabis. It's a personal fascination of mine, and I think that some of the most interesting chemistry that takes place in the plant is with the terpenes. So to begin with, why do we care about terpenes? Why is this interesting? Well, I always liken the cannabis experience to drinking wine. You don't go out and buy a $200 bottle of wine because it has 15% alcohol in it, right? So for the longest time in the beginning of the industry, it was all about THC concentration. Well, THC is not necessarily what causes all of these sort of residual entourage effects, right? It's not what makes the user experience interesting. Just like you wouldn't judge wine by its alcohol content, you shouldn't judge your cannabis flower by its THC concentration. So I saw this very interesting statement from SC Labs a while ago where they had tested all of the different winning cannabis crop strains. And the winners sort of unanimously had very unique and interesting profiles, which I thought was pretty fascinating. So they did all the testing, and across the board, the THC concentration was relatively the same. But the winners really had this very sort of fascinating terpene profile. Well, so in the cannabis flower, there's, depending on who you talk to, anywhere from 140 to 250 different terpenes that are present. I don't know that there's really necessarily a consensus about that, but there's a lot. So I often say 200 because it's right in the middle. So I get both sides to agree with me. The science of testing for, really anything in cannabis has evolved so much in the last 10 years or so. And so to see this evolution, particularly in terpene analysis, is pretty amazing, right? So we're going to go through some methodologies now. And then I'm going to talk a little bit about the chemistry of cannabis and sort of the science of doing this testing. So first of all, terpenes are secondary metabolites that are produced through the MVA and MEP pathways. This also follows the cannabinoid synthase in the cannabis plant. They are built from these 5-unit carbon molecules called isoprene. Their designation is a monoterpene, a diterpene, a sesquiterpene. These are all indicated by the number of 5-unit isoprene molecules that make up their structure. I talked about this a minute ago a little bit. The entourage effect, which is sort of the secondary body high that you experience while you consume cannabis, right? So people talk a lot about how certain strains make them feel sleepy, or certain strains make them feel paranoid, or bring euphoria about. So because of this metabolic production, it's not much of a far leap to assume that there is significant interaction with the endocannabinoid system and these molecules. So there seems to be a lot of strong evidence that it goes beyond just sort of a flavor experience, right? So some people really love this, purple Urkel is amazing, it tastes so good, it makes me feel this certain way. And then why does this other one make me feel paranoid and negative? And so it's, there's a lot of research that's being done to sort of quantify these specific physiological responses. And I think in the coming years, you're going to see a lot of that research point back to terpenes. Now we're going to jump into the analysis of terpenes. Typically, this is done by gas chromatography. You can also do it using liquid chromatography, but as it's a volatile compound, gas chromatography is really more appropriate for this. This is the setup that we use. So I'll get into why I love Headspace so much. But for those of you who don't know, this is a Headspace sampling system. Middle instrument's a gas chromatograph. And then we use mass spectrometry for detection. So before we do any detection, we got to get our samples ready. Now, those of you who have testing labs in California and understand the very convoluted BCC regulations, they state that we have to use 500 milligrams of samples. So one of the benefits of Headspace is that you can actually analyze your sample directly. Now, if I take 500 milligrams of cannabis and I put it in a Headspace vial, all of my peaks are going to be saturated. So we have to do a dilution, and that's purely regulated by, the state regulations. One of the downsides of doing this too is, as you well know, every form, every matrix of cannabis that you can think of exists in some form, right? So just because you have a method that works strictly for flower, like I can take my flower and put it in there, and there's not a tremendous amount of matrix effects. If I take oil and put that in a Headspace vial and analyze it, there may be significant matrix effects. So doing an extraction is beneficial for all the different types of matrices that you see out in the market. So we take these 500 milligrams, we put it into a sample vial, we shake it up, we crush it into powder. So we use milled beads or agitation. And so once it's ground sufficiently, sometimes people will use cryo mills or they'll just shake it. Then we use IPA or methanol, depending on which solvent you prefer. And we do fill the volume to 10 mils, and then we take a 20 microliter extraction from that, put it into a Headspace vial, and we do what's called total evaporative analysis. So everything in that Headspace vial is in the gas phase. So again, here's a small example of the number of matrices that you see out in the market. Butane extract, which people always ask me, they go, do you have an SOP for extracts? I go, well, okay, you take a look at butter, right? It's structurally and chemically much different than a butane extract versus a CO2 extract. So no, I don't have 800 different SOPs for, sample extraction, but we have some general ones that work pretty well. I've seen dog treats and lotions and toothpicks and every sort of cannabis product that you can imagine has come through our labs. Traditionally, and I did this for 10 years before I started working heavily with Headspace, we would do liquid injection. So you have to do an extraction, you pull out 1 microliter, whatever your sample volume is, and you drive it directly into the injection port. The problem is that cannabis is incredibly dirty, right? There's over 1,000 compounds found in cannabis. You have waxes and lipids, THC, right? 20+% THC, 80, 90% THC in certain extracts. So you have this huge concentration of other analytes, right? So the advantage of using Headspace is that we largely leave most of that stuff in the vial, right? So we can dictate a specific temperature at which we're bringing this vial up and doing our injection. So anything with a boiling point below that stays in our vial. Everything with a boiling point that we want to look at is in the gas phase, and we can do an injection. So you can see here, this is contamination, right? So we actually don't even use a glass wool liner in our injection port. But if you do liquid injection, you have to do that. So here's an example of your liner after 7 injections. You're changing those liners a lot. So the maintenance that goes along with liquid injection can be very problematic. There is certain advantages to it, but Headspace really is hugely advantageous. Although I'm not going to discuss it in this presentation, you also can do this for residual solvent analysis. In fact, you can run residual solvent analysis simultaneously with terpene analysis, which wouldn't necessarily be possible or practical with liquid injection. So here's an example, right? So a lot of flower research is done with direct analysis. So I can take a sample, I can put it in a Headspace file, bring it up into the oven, and I get all of those volatile compounds to come off. So this technology is used a lot in environmental analysis. So when they look at like VOCs in water or soil, they're able to analyze those samples directly, which is fantastic, except there's so much analyte that we want to look at in our cannabis sample, it makes it very problematic, right? So terpenes, depending on the strain, you're looking at 3 to 5, 6% by weight of this, of our target analyte, which is significant. You don't want to shoot that onto your column. It's going to totally overload your mass spec. Although it is very advantageous for things like gummy bears or lotion, which are hard to extract, and that matrix does work well in Headspace analysis. Things like oils, you can tend to get very poor recoveries depending on the analytes. So heavy boilers like alpha bisabolo tends to not want to come out of these viscous oils. So I did this very cool research project where we got certified reference material from Emerald Scientific and ran all sorts of different tests, all sorts of different extracts to sort of look at the extraction efficiencies of these different analytes. So these heavy boilers, we were getting about 10% recovery from a direct analysis. And then we did a DMA methanol extraction, and we were up to 90% recovery. So here's a slide showing sort of the theory of Headspace analysis. So, for example, if we're looking at terpenes, you can run your Headspace at 130, 140 degrees C. Anything that has a boiling point above that is going to stay in your vial. So when we do our injection from the Headspace of the vial, all that stuff is left behind. It's ultimately a much cleaner analysis. Now in California, we do this total evaporative analysis. It's also called total evaporative technique, where we are doing an extraction and we spike either 10, 20, 40 microliters of analyte into our vial. So this is a very useful technique, particularly because in your Headspace unit, you can dictate how long you're making your injection. So you can adjust your sample volume. So if I want to inject more sample onto the column, increase my detection limits, I'm able to do that. There's other problems that come with that, but it is a flexible methodology. Now, for a long time, terpenes were traditionally analyzed using GCFID, so a flame ionization detector. But as sort of the science of cannabis and terpene analysis has evolved, it sort of creates this ambiguous analysis. So if you're trying to analyze 140 different types of analytes, using an FID is not necessarily practical. So the people that I know that run it, their run time is 60, 70 minutes. All right, so our run time for our 21 terpene method is 9 minutes. So you're more than 6 times more efficient using a mass spectrometer. Also, you're able to get spectral data, which is very useful in determining what terpenes I'm looking for. So if I want to look at unusual terpenes, you've got to have a mass spec. Generally, for production style labs, we do either 21 or 42 of the most common terpenes, because generally there's about 17 that people really tend to care about. And in more research settings, we can, add a ton more. I know of an individual that runs a 70-minute method to test for 140 terpenes, which is not always practical, right? If you're in a production style environment, you're not going to run 18 samples a day. It just doesn't make sense. We tend to, step back and focus on these particular terpenes that people sort of care about. You see them a lot in labeling. Well, here's a chromatogram from our 42 terpene analysis. There's been right around 200 terpenes identified, lots of sort of cool and unusual ones. I spent a lot of time doing research on terpenes before I started doing this job. So we were looking at manipulation of terpenoid production in cannabis, right? So the idea is, if I could always create sort of these amazing strains of cannabis, it would be, I mean, that product would fly off the shelves, right? So, you know, if I could turn $2 bottle of wine into a $100 bottle of wine relatively easily, right? If I could always create these fascinating and amazing terpene profiles from my plants in a consistent way, I would be hugely beneficial. The terpenes are very easy to calibrate and very difficult to truly measure. And the problem is that they share masses, right? So they're structurally very similar. They're all built out of these 5-carbon isoprene units. So you see very similar masses. 121, 136, 93, 69 is present in most of these terpenes. So if you have co-eluting peaks in FID, you're just going to see a single peak. You're not able to isolate those by mass and mass ratio. We usually do a calibration from about 2 ppm all the way up to anywhere from 500, 1,000. They tend to be pretty linear across this range. If you're looking at rare, unusual terpenes, you can go lower. They tend to make just beautiful looking calibration curves, which is really pretty nice. But then you have to sort of sort through this massive amount of data that comes back. There's not really a catch-all method that's easy to analyze for potentially 200 analytes. One of the problems too with running these kind of analysis is that you get all these matrix effects like we talked about earlier. And I talked a little bit about a research project that I did looking at these, and the oils seem to be particularly problematic. There's something about there's some chemistry in which they love to bind to these heavy boilers. So you get like beautiful recoveries from the first part of your run, and then at the end they just drop down to nothing. So I've run through, those of you in California, I don't know if anybody's going through validation right now, but it is not a particularly fun experience. I've gone through validation a couple times with different labs and doing with terpenes and residual solvents, but focused now on terpenes. They typically include running precision, accuracy, matrix spike recovery, LOD, LOQ. So this stuff is, terpenes tend to recover pretty well, particularly with flower. Again, a little more problematic with running oils, but we have ways around that. Again, here's some data that we ran for precision and linearity. And so we run these two different, right? So we run a spec standard, 42 terpenes, and ResTech standard, which is 21. And then depending on the lab and their needs, sometimes they will add in individual terpenes. So I get this question all the time, like, how many terpenes can you analyze for? Well, how many terpenes do you want to analyze for? How many calibration curves do you want to have, right? That number is, it goes on as long as you want it to. So in closing, Headspace, gas chromatography, mass spectrometry really is the cleanest, most effective technique to analyze cannabis products for terpenes. I've had customers run for multiple years without cleaning or changing their columns, which I suggest that you don't do, but it certainly can be done. It's sort of a testament to how clean this process can be. I have some digital copies of application notes relating to this that are available. So after the presentation, if you want me to send you one, I can give you my card. And if you have any questions or comments after this, if you don't catch me, you can contact me at adam.floyd@PerkinElmer.com. And a special thanks to the PerkinElmer Cannabis team and Lee and Tom for helping me with all of this. So I think I talked a little too fast and flew through my presentation. So we got time for some questions if anybody has any. Which slide? Oh, yeah.
So I have a question.
Yes.
I'm over here. Hey.
There you are.
Hi. So you indicated that in the plant you see about 1% total terpenes in there. When you're working with commercial vape oils, what's the range of percentages you routinely see?
So in flower, we typically see between 1 and 5, depending on the strain. And in commercial vape oil, you see between 0% and 60%.
60?
Yeah, I mean, the range is significant, right? So when you look at food, right, so if they prepare like CO2 oil, there tends to not, like when you are formulating oils into cannabis products like brownies, you don't want it to taste like a bud, right? So they tend to remove all the terpenes, and so it's just pure isolate. But you can see in certain extracts, 20+% is not uncommon.
And just one follow-up question.
Yeah.
Do you see a difference in the terpene profile if you extract it by butane versus CO2 versus ethanol?
Yeah, absolutely. So all three of those have different capacities to solvate terpenes.
What do you think is the best way to protect the terpenes?
So butane extracts tend to be the highest concentrations from my experience, right? So ethanol is problematic. You can pull chlorophyll and a lot of other things out with ethanol, but due to the hydrocarbon nature of butane, you do I think that it preserves what they call sort of the chemovar, or the chemical fingerprint of the plant, the best.
Thanks.
Oh, you're welcome.
Hi, Adam. Thanks
Hello.
for the information.
Of course.
Wes Burke here from Emerald Scientific. The last round, the spring round of the proficiency test, the interlaboratory comparison component showed quite a bit more deviation and quantification of terpenes than we'd like to see, especially acknowledging the importance of these compounds in the outcome. There's been some conversation and speculation about what the industry can do to improve it, and obviously I think these kinds of conversations go a long way towards that. I'm curious if you think that simple run times versus a lab's profitability come into play in an equation like this.
Yeah, so that's always, there's this difficult contrast between doing really, really good science and making money, right? So production labs, they have a big overhead. They don't have the luxury to run a 70-minute method. So I do think that is partially problematic. So from my experience with the Emerald PT tests, they come in an oil-based matrix, which is very difficult to efficiently extract. So I think that I've done a lot of research with different combinations of extraction solvents. And I think that there is one that is generally the most efficient at pulling the majority of these compounds out of this oil, right? So if you do a strict methanol extraction in oil, you'll see about a 10% recovery, 10 to 15% recovery for the heavier boilers. If you add a little DMA in there, it suddenly jumps to 80 and 90%. So I don't think it's an instrumentation issue. I think it has to do with sample prep. And I tell people this a lot. 95+% of your problems happen before you put that vial into your autosampler.
Hi, you did 42 terpenes. How many do you think is possible that you could do?
So I've seen 140 that have been run. So the problem comes from A, finding commercial standards, and B, making a calibration curve with 200 or 140 calibration curves, right? So really as many as you want to run. For a lot of the commercial guys, they don't really care about most of them. They're not interesting, right? They care about the 17 big terpenes. Those are the ones that people want on their labels. So to answer your question, is as many as you want.
Thank you. So my question is twofold. One, what percentage of the products you're testing are actually requesting the terpene test? And because the BCC backed down on the industry's pushback from cost perspective, what's being done to bring the cost down so that terpene profiling can be affordable and we can see that in the dispensaries?
So interestingly enough, I feel like the terpene requests for, have dropped down significantly. So a lot of the feedback, right, because it's not a required test. So you're paying to put something on your label which can potentially put you in jeopardy. Some people don't, and to your point, I think that it's very valuable information. One of our focuses is a very quick runtime. Another alternative is combining the two methods, right? So you're always testing for terpenes and residual solvents. So I think that really easier regulation and faster runtimes can help drive that cost down and promote people wanting to do it.
And just to ask about another added level of complexity in the terpene world is the isomer differences that I'm not sure the field has really embraced yet we know in certain cases linalool, I think, has different bioactivities depending upon what the isomer is. Beta-caryophyllene, we were just talking at break, has different bioactivities depending upon what the isomer is. So what do you think the field should do to embrace inserting isomer standards into this technology?
That's a very great question. So we do see separation of isomers. I think education is the key there, right? So if people don't know what they want, they're not going to ask for it. And laboratories are not going to give people information they don't want. So I think that education really is the key there. We do see like cis and trans neurolidol. People, they're educated about those and they request those tests, but they could care less about beta-caryophyllene, right? But I think that further education helps to bring those issues to light, and I think that the bioactivity of that is super fascinating.
Hi, my question's about pyrolysis studies. So do you have any recommendations if a lab was to be interested, for example, in studying different degradation and combustion compounds in a smoke medium compared to a vapor medium, and what's your take on GC as an instrument for parsing out some of the, let's say, the degradation products and the product cascades that might come from combustion?
Yeah, I think that's totally a great idea, right? I've had a lot of conversations recently, especially with sort of the vape scares. They have devices hooked up to a GC. I think it's the appropriate instrument. I think a GC triple quad would really be ideal for this. So they have devices that simulate smoking, right? So they use these for cigarette analysis, what's showing up in cigarette smoke. And I would love to create a hyphenated system with this technology, right? So you basically can measure what a single lungful of smoke from a joint or or vapor from a vape pen contains. And so, you would be able to see the degradation products, right? You measure the raw product and then the vape from it, and you could compare the two and see how much of it is sort of retaining its integrity.
And is PerkinElmer looking for any DEA licensed labs to do these studies?
Not at the moment. Not that I'm aware of.
Maybe you don't know you're looking.
Right, exactly right. Okay, I think we're good. All right, thank you guys so much.